Alright, this provides the solutions for the two problems that you were assigned to complete by Wednesday. This is number 42 and number 44 from page 40 and page 41. So we're going to start with number 42, which says a stone is thrown vertically upward with a speed of 18 meters per second. So we've got a stone, and it's thrown upward. It has an initial speed of 18.0 meters per second, and it gets thrown vertically upward. We want to know about this stone. A, how fast is it moving when it reaches a height of 11 meters? So that means that when we get to a point 11 meters above, that's going to be our y value. We want to know at that point what is the velocity going to be. So our givens in this situation are the initial velocity of 18.0 meters per second, our height in the y direction of 11.0 meters high, and we have to consider what else we know in this situation. We don't know the time. In fact, that's actually what the problem asks us to solve for B. But we do know that this stone is being thrown in a vertical direction, so we can neglect air resistance, and we also know that since it's thrown in the vertical direction, nothing is changing its motion with the exception of gravity. This stone is in free fall, so we know gravity has a value of 9.80 meters per second. Now we're going to establish our axes. I'm going to keep things simple for this problem. I'm going to say that for this problem, up is the positive direction, which means that our gravity, which is always toward the center of the earth, is negative. That gives us the ability to have our y value set in the positive direction and our velocity set in the positive direction, and only our gravity in this situation is in the negative direction. We're trying to find our velocity at the top. So a useful equation to use would be the relationship between these values, which is going to give us v squared equals v naught squared plus 2gy. The relationship between position, gravity, and initial and final velocity. And then we can plug in our values to solve. So v squared is going to equal 18 meters per second squared plus 2 times negative 9.80 meters per second squared times 11.0 meters. Alright, in order to solve, we're going to take the square root of both of these sides, so that means that the velocity is going to equal the square root of, and here you want to systematically solve, 18 squared is 324 plus, and then this is going to be how the units meters squared per seconds squared, and it's going to be plus, but I take a look ahead as I'm problem solving and I notice that there's a negative in here, so the whole value over here is going to be minus, and it's going to be 2 times 9.80 times 11, and that's going to be 215.6, and that's going to also be meters squared per second squared, which thank goodness, because I can combine those units. So that means that velocity is going to equal the square root of 324 minus 215.6, or 108.4 meters squared per second squared. We take the square root of that, and we end up with a velocity of 10.4 meters per second. Now, here's something that I want to stop and talk about directionally. Right? This was velocity squared, and this value over here is a square root value. So that means that this answer right here is the absolute value, and the absolute answer What it really gave us is it gave us plus or minus the velocity equaled plus or minus 10.4 meters per second. Remember that that is a mathematically factual statement, but we can use what we know of the situation up here to determine which is the more correct answer. And in this case, we set our axis so that up was positive and down was negative. We wanted to know what the velocity was when the ball went from the bottom to up to 11 meters. That would be traveling in the positive direction with a positive velocity. So the most correct answer that we could give from this factually mathematically correct value right here would be 10.4 meters per second. And that's just going to be correct. We know it because we set our axis, so we know that that is true. All right, so that's solving for A, the velocity up at that point. B asks us to find the time that it took to get there. All right, so in this case, the velocity becomes our who cares value, and we're trying to find the relationship between initial velocity, displacement, acceleration due to gravity, and time. And then we're going to use the equation y equals v naught t plus 1/2 gt squared. Alright, if we plug in for this equation, one of the things that we're going to notice right away is that 11.0 meters equals 18.0 meters per second times t plus 1/2 times negative 9.80 meters per second squared times time squared. We've got a time squared and a time, and we've got another value. So we're actually going to be using the quadratic formula to solve this problem. So that means that in order to solve for time, we're going to have to set it up so that the whole equation is equal to 0. And then it's going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, I'm going to go ahead and do this, and I'm going to set up the equation equal to 0 so that when I rearrange, I'm going to resolve this right here so that it's negative 4.9, and I don't want my a value to be negative, so I'm going to rearrange everything onto this side of the equation. So that's going to be 4.90 meters per second squared times time squared minus 18.0 meters per second times t plus 11.0 meters equals 0. Now I have very conveniently my a value, my v value, and my c value. And when I plug them into the quadratic formula, I'm actually going to drop the units. So let's go ahead and do that. Let's set it up so that t equals 18 plus or minus the square root of 18 squared, that's 324, minus 4 times 4.90 times 11.0, that's 4ac all over 2 times 4.902a. Alright, and when I solve this quadratic formula, I know I'm going to get two answers. T1 is going to be 2.90 seconds, and T2 is going to be 0.775 seconds. And so now I have to decide which one is more correct, and I have to think which one is more correct. And I have to go back to my situation again and think this through. Alright, when I throw the ball up, it's going to make it to 11 meters, which means that both values are valid times because the values are both positive. But in this case, I have to decide which one is the value that I want. So I have to consider the situation. It's going to move up until it gets to 11 meters, and then it will continue to travel up until the velocity is 0. And then it's going to come back down. And when it comes back down, it will again pass this time 11.0 meters. So that's what these two times represent, and this is also the answer to part C. The reason that we have two different times is because the ball passes that 11 meter value twice, once on the way up and once on the way down, which means that our answer, the time that it first hits the 11 meters on its way up, is the sooner time, the 0.775 seconds. And so that takes you through the solution to A, B, and C for number 42. We're going to go ahead and we're going to move forward and we're going to solve problem number 44 as well. Problem number 44 is a level 3 type problem. If you would like to look at other problems like this that are also level 3 type problems, it just happens that 45, 46, 47, and 48 are all level 3 problems that allow you to use the kinematic equations in a situation of free fall. So let's take a look at the situation on page 41. Number 44. It tells us that a falling stone takes 0.28 seconds to travel past a window that is 2.2 meters tall. So let's sketch it out. Alright, so you've got a stone that falls, and we know that that distance, alright, the value there is 2.2 meters, and that's actually your delta y right there. And that time that it takes is 0.28 seconds. So a few things that we need to consider in this situation is that we are given that your y is 2.2 meters and that your time is 0.28 seconds. The stone is in free fall. So if the stone is in free fall, that means that gravity is working on it. And gravity has a value of 9.80 meters per second squared. That's an acceleration. Now we know that gravity is always toward the center of the earth, so it's time to set our axes. In this situation, I'm going to set the downward direction as positive, so that way my y displacement can be a positive value and my gravity can be a positive value, which means that I'm just set my axis opposite to the way that I usually do. And what I'm ultimately trying to find is the height above the window that the rock was dropped. So what I'm actually trying to find in this situation is I'm actually trying to find the point at which the rock was released. I'm trying to find a position, and I'm trying to find the position at which the velocity of the rock was 0. And so let's think about how I figured out that that's what I want to find. I want to figure out that where the ball was dropped or where the rock was dropped, and in order for me to do that I have to kind of zoom back in my head to what's going on in the situation where the rock is being dropped. And if the rock is being dropped from that point, then that means that that point was the slowest that it was moving, and ever since then gravity was working on it, causing it to move faster and faster and faster as it moved downward. So that means that in order for me to find this, I'm going to have to work backward. And since I'm finding how high above the window, then that means that the reference point that I'm going to be working from is actually this point. So I'm going to be comparing this point to some point above it, which means the more I know about this point, the more helpful it's going to be. And I need a connecting point. I need something that connects this point to the values above it. And so what I'm going to try and find for that point is I'm going to try and find that velocity. So I'm going to use these numbers right here to find this velocity. And so I must consider, since I'm moving in the positive direction downward, that what I'm actually trying to find first is the initial velocity for these values, for the position change of 2.2 meters, for the time interval of 0.28 seconds, for a gravity of 9.8 meters per second toward the center of the Earth. So I'm going to find the relationship between this velocity right here, which for these variables is the initial velocity, and that means that I should be using the equation y equals v naught t plus 1/2 gt squared. So lucky for me, in this situation, I'm not trying to solve the quadratic formula. I have time, so I'm going to plug in my knowns. 2.2 meters equals v naught times 0.28 seconds plus 1/2 times 9.80 meters per second squared times 0.28 seconds squared. So at this point in time, I'm going to isolate my variable and I'm going to solve for v naught, and I get that v naught equals 6.485 meters per second. And you're going to notice that in solving this, I went ahead and I kept more significant figures than necessary because I haven't found my final answer. I haven't found the position at which the velocity of the rock is 0, the position at which the rock was dropped from. So now I have this value right here, the velocity of the rock when it was there, and now I have a connecting point. I have a relationship between this reference point right here that will allow me to figure out, well, how high up was it? Alright, so using my connection point, my situation is now that I have some point at which the rock was dropped, and now here's the top of the window. I know that at the top of the window the velocity was 6.485 meters per second. I also know that gravity is acting on the object in the downward direction. I don't know what this position change is, but I do know that up here at the top the initial velocity was 0 meters per second, because that's the point at which the rock was thrown. So now I reconsider my givens. The givens that will help me find my ultimate answer. The initial velocity is 0. Acceleration due to gravity is 9.80 meters per second squared, and I'm actually going to keep my down is positive axis. I know that the final velocity was 6.458 meters per second, and I'm trying to find what the displacement is, or how high above the window the rock started. So now I'm looking at this relationship, and what I'm gonna do is I'm actually going to use an equation that gives me these relationships, and so that's going to be v squared equals v naught squared plus 2gy, where I'm going to solve for y. And so that's going to be pretty simple. That's going to be 6.458 meters per second squared equals initial velocity is 0 plus 2 times 9.80 meters per second squared times y. And I would, I'm going to isolate my y value, and my y is actually going to be equal to 2.1 meters above. Right, because this displacement right here was 2.1 meters. That's what that value right here represents. And so this is a really good example of what a problem with a connecting point looks like, and hopefully you found that solution helpful.